It is always a pleasure to introduce our friend, this engineer scientist who has made his mark in the world, but he is now making a greater indelible impression by answering one of the major questions that have been asked for the last 2 or 3 generations. Is it possible for a monkey or a horde of monkeys to somehow accidentally pounding away on typewriters produce an Elizabethan sonnet? Well, that's been a question that the evolutionists have smiled and said, given enough time, they certainly could. Therefore, given enough time, living systems could evolve. That has been their plea. But I think you'll find after the lecture that has become their plight, because he's going to solve this scientifically in honor of the Creator himself. Would you welcome our engineer, Jim Hoff?
One of the things that I think people don't have a very good grasp on is probability. And it's okay when you're talking about whether the weather is 20% chance of rain or something like that. We don't have a hard time. That means it's got a 1 chance in 5. Everybody understands that. But when the numbers get very large, we lose our ability to be able to really understand what those numbers mean. And so what I'm doing is trying to give you a grasp of what happens when the numbers get large, when the likelihoods get very great or very small. What does that mean? So I'm going to be doing some things with cards, and I'm not a big card player, but probability is not only something that you use at a gambling place. In fact, it's major use. Scientists use it. You use it every day, many times without even knowing that you're using it. Whenever you find yourself saying, what's the likelihood of that? You see an old friend, someone that you didn't expect to see in 20 years, and there they are at the grocery store or something like that. What are the chances of that? Sliding down Mount Improbable, and of course, I named this after a book, Climbing Mount Improbable, written by Richard Dawkins, and he's trying to make the case that improbable things can happen. Now I want to show you that improbable things don't happen. And now why would this be the case, that they would want to try and say that improbable things can happen? In the secular world, the assumption is that evolution occurs. You will never see anybody doing a serious questioning of whether or not. Now there are exceptions. There are some scientists who have signed papers saying that they question evolution, for example. I think it was 1,000 of them. But in general, they're not questioning. They want to know how evolution happened, but not whether evolution happened. And if you ever have a chance, go to Wikipedia and look at the Origin of Life webpage. And it says, so it's called abiogenesis. Biogenesis is what Louis Pasteur did. Abiogenesis is what they're doing now to try to figure out how life happened without God. And so on there it says, abiogenesis is the study of, I'm paraphrasing, the study of how life, the natural process by which life came to be. Now that's, you've heard the saying, have you stopped beating your wife? That assumes that you're beating your wife, or we're beating your wife. In the same one, the natural process by which life came to be assumes that life did come to be by a natural process. We in our camp would say that that's not the case. But this is an assumption, and it's called the methodological naturalism presupposition. This is not something that is derived from science. It is something that you decide to put on, and when you put on your lab coat, you say, I am not going to allow, I'm not going to examine supernatural origins or causes for natural events. Now, of course, science is all about natural events, right? You don't study how many angels can dance on the head of a pin in science. That's a theological question. The interface here, when you have a natural phenomenon like the origin of life, and you have to know whether or not how to explain it. And if you say we're not going to allow supernatural explanations, what does that mean? What does that mean? That means that, for instance, if you were a scientist and you were going to go examine the supposed resurrection of Jesus, you would allow for the swoon theory, which is that Jesus did not die on the cross. He merely passed out and went into the tomb, and then he somehow rolled this huge rock that takes 10 Roman soldiers to remove that out and so forth. Or you could do the replacement theory, which is what the Muslims usually believe, that it was not Jesus on the cross. Anything but the resurrection theory, which is that Jesus, because that's supernatural. Same thing with the crossing of the Red Sea. These are things that the supernatural explanation is not allowed. But so that's why we're in the situation where we want to try to examine the probability of these things, and the evolutionist side, they don't want to examine it because it happened. So if you have any evidence that goes against that, it's just going to be ignored. But it is important to look at these kinds of evidences that actually do occur. Okay, I'm going to tell you a little bit about what information is, at least what it's going to mean for me, because I'll be talking about a special kind. It's most of what you would consider information, and that is complex specified information. Specified means that, if I were to show you, if you were to look at this picture, for example, and there's little data bits on there, that is a picture. Well, that's not a good example because it's actually showing something. This is specified information. If you're looking at the old TV picture that before we had digital, and you turn on the TV and it would just be what they call snow, that's information. If you wanted to know what all those dots were, it might be worthwhile for you to record them and record what they are, but that's not specified information. It isn't information that points to something else. Now, another type of that's non-specified information is what was the temperature yesterday. When you find out the temperature yesterday, it's not going to tell you how to build a car or anything like that. It's going to tell you what the temperature was yesterday. That's not specified information. Specified information is something that tells you it tells you something that's totally what's called orthogonal. It's not related to what you're working on. For example, what's written in a book. If you have a book and it's got one of Shakespeare's sonnets in there, the information there, you can't learn anything about that information by studying the paper and the ink and the manufacturing process. All those things will not tell you what the information that's written in the book. That's what we call specified information. DNA is specified information. It's like a hard disk. It's got things written in there that tell you how to build and maintain an organism, a human body, a lizard, a fungus. They're all using DNA as the thing that supplies the information. That's what specified information is here. So let's see. Wikipedia says information can be thought of as resolution or reduction of uncertainty. When you get information, it tells you that between the possibilities this and this is the one that happens. Okay, so now you're not uncertain about it. Now you're certain that this is the case. So there's a light switch on the wall, and it could be up or down. I can't see the light switch, and I say, what's it in? You say, it's down. Okay, now I know one bit of information. One bit of information differentiates between two equally probable events, possibilities. Now, if I were coming into the room and it was dark in there, and didn't know what position the light switch is, it's probably in the down position, right? So if you tell me, if I go over and check the switch and say it's down, you haven't told me anything. A little. You told me a very, very little. If you told me it's up, I go, wow. It's called the surprise factor. This switch is not in the position that I expect, and so it's conveying more information than what you would think. That's why I say it's got to be equally probable. You can't have any presuppositions or pre-information about what it is. That's what information is, and it can be measured. We have a unit of measure. Everybody know what the unit of measure is? It's a binary digit, a bit. You use it all the time. I know all of you do. When you go to the store and you buy a computer, you want to know how many megahertz it is. Well, that'll tell you how many bits it has. You buy a hard drive, it used to be 20 kilobits. Then they went megabits. Now they're in gigabits, and now actually we're into terabits now. Terabits, which is 1,000 million billion trillions of bits, I believe it is. So incredible amounts of bits. But one way to look at this is, when you were little and you were a 3-year-old and your 5-year-old comes up to you and he says, and you've got a dime in your hand, and he's got a penny, or I've got a penny. And I say, I'll trade you this big penny for that little dime. And of course, bigger is better in the eyes of a 3-year-old, so they'll gladly trade it. But there's a value there that goes beyond that that the 3-year-old hasn't learned about. Well, it's kind of that way with what we learn about here in science. We started out measuring the mass of something, and the more massive it is, the more kind of the better it is. When you want to buy a car in the 1950s, a bigger car is a better car, it's a heavier car, and so forth, and that makes it a more expensive car, a more valuable car. But then now we started worrying about other things, and so that's mass. Now you start worrying about miles per gallon. That's energy. And that's a whole new thing. And I don't know if you remember when you first learned about energy, but what is this? It doesn't have a weight. It doesn't have, and when you want to buy a battery, you want a smaller battery which weighs less, rather than you're willing to pay more for the lighter battery because it's got more energy. See, that was another level, mass and energy. Well, this is a third level. We're now in the information age. And what you want is something that has almost weightless, right? And it takes no energy, and they work very, very hard to be able to do that. But you want it to have lots of information capability. One of the things that I just recently started working with was what they call an Apple. You put it on your keychain, and you can find your keychain. You get on the internet, and it's continually putting out a ping. And it's got a battery in it, but the battery lasts 10 years because they made it so light and so, they want it small and they want it light. And this thing just every 10 seconds goes ping. And any iPhone within 100 yards will pick up that ping and say, okay, I just got a ping. Send it up to the cloud. Apple keeps a database of those things. And so if you want to know you've got a stolen thing or you've lost your phone or whatever, it'll be up there on the cloud and it'll tell you where it is, and you can drive to, it'll be anywhere in the world, but it's probably in your bedroom, And but see how that works. Energy, our information is the age that we're in, and that's what we really want to spend our energies on. In fact, there are now people who believe that information is the basis of all being. That it isn't matter and energy, but information is the basic. I haven't studied that enough to know what that's all about. But that's one of the most recent ideas. Okay, well anyhow, let's go on. Information is improbable because it informs you of a normally unlikely situation. The more unlikely the situation, the more information is contained in the message. So when I tell you something, if I tell you, you probably were a little bit surprised when you heard that my birthday is July 4th, right? Because not many people have the birthday. That's the best birthday you can get, right? You don't want your birthday on Christmas. You don't want your birthday on Thanksgiving. It doesn't come every day at the same time. But New Year's, you got other things you're involved with. But July 4th is great. As a 3-year-old, you go out to the parades and everything else. But anyhow, that's very unlikely. Now, if somebody comes to you and tells you their birthday is on February 29th, you go, wow, that's really cool, right? It's 4 times as unlikely as any other date for your birthday. Now, when you get 2 people that meet each other, and you say, my birthday is February 29th. Hey, that's my birthday is the same one. There's a big wow factor, which is with 365 times 4 is 720, about 1440, somewhere in that range. Chances are 1440 of this one, 1440 of that one, and the two of them is 1440 squared, which is over 1 in a million. People who are you see how that works? The surprise, that's actually what they call it, is the surprise factor. The more unlikely the situation, the more information is contained in the message, and the more you're being informed. Okay? Information can be measured, and the common unit of measurement is the bit. There are other forms of it. There's a base 10 form, and there's a base pi form, a base E form, but they're all telling you the same thing. You can convert from one to another just like you can between inches and centimeters. But the bit is the easiest one to remember. It's telling you two things that are equally probable, and you're telling which one it is. And so you gain 1 bit of information. Now, as an engineer, when I was a new engineer, we would actually bootstrap the computers with a string of switches. That's what they meant by bootstrapping. Bootstrapping is you're pulling yourself up by your bootstrap, and we would have to flip those switches into the right. What it would be one command. It would say, go to this address and go get your data there, and then the computer would bootstrap it that way. Well, if you have 8 switches, how much information are you getting? I guess I just told you, it's 8 bits, right? But how unlikely is that? It's 2 times 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 2, 8 times. and that's 2 to the 8th power is 256. So you now have 256 possibilities that you can give there. Now, the switches, we had more than that because it took more than that to tell the computer where to go. But you get the idea. The more unlikely the situation you want to explain, the more bits you're expressing. Okay? The bit is actually a measure of probability. Each bit of information cuts the probability in half. And if you go on Wikipedia and you look up the word bit, it'll actually tell you that. It's a probable thing. We're actually dealing with probability just in the information in the thing that we specify it with. Okay. Specified information, which is what I've been talking about, is information that informs you on something unrelated to the medium that carries the information. So you may have a movie that you want to watch. That movie may get recorded on a microphone and a television. It'll go through a coaxial cable. It's still information, but now it's an electrical encoded in some agreed-on format that the transmitter and the receiver know, and it gets transmitted from one end to the other. Then that will take it and store it in a memory. And that's still information. It's in a different memory. It might be in memory cores. It might be in you see what I'm saying? It gets changed. You could take it and you could put it out on a smoke signal. You could out there with your blanket and you could send the signal with smoke signals. Anything. It's still the same information. You see how that works? And information, we want it to be in the simplest, cheapest, lowest energy, lowest mass capability, and we're getting it. I mean, every generation gets. Our kids don't realize how we had to live without cell phones. They can't imagine that we would ever get by without cell phones. Okay, so here's an auto repair manual. You can study the ink and paper in an auto repair manual, and you're not going to tell anything about how it tells about an auto repair. That comes and is imposed upon the paper and ink by an intelligent agent, which is us. There's only 2 intelligent agents that we really know of anything for sure, and that's humans and God. Okay, but there is the possibility it could be ETs, and that's a whole theological thing. I don't believe there are extraterrestrials. For theological reasons. If they're living in a fallen world that was cursed by Adam, that wouldn't be fair. That wouldn't be right. God wouldn't curse them by having them live in a world that was cursed. So that's one of the big reasons why I don't believe that we'll ever find extraterrestrials. Okay, telephone book, same thing. Computer operating system code or a program. This would be another example. A message from space aliens, as I mentioned. DNA, okay? DNA is specified information. In spades, it is the most dense form of information that we know of. I think we've come up with some other ways that we could possibly do it. But to think that it's done with what do you call them? Bases. Put together with chemicals, just atoms for each bit is just incredible. But that's the way God did it. One can study ink and paper or the chemical characteristics of DNA, and nothing will be learned about the specified information contained therein. Now, that's one thing to take into account. Some of you have heard the Miller-Urey presentation that we had here recently. And the Miller-Urey, they're talking about the fact that, wow, in 1952 we figured out that you might be able to produce amino acids. They have to be left-handed, and they get equal left and right, which is a problem. But even if all that happens, the information is not there in those amino acids. That's just the paper, That's what you're writing the information on. And they haven't even gotten to the point where they're actually putting the information into the amino acids. That's where the real breakdown happens. Okay? What is entropy? I don't want to maybe I shouldn't go into this, but it's basically a very similar thing. Entropy. You probably have heard about the second law of thermodynamics, which says that entropy only can increase, which means that the universe is going into a more likely situation, basically is what it means. There's energy and there's useful energy. If the whole universe was at 74 degrees, it's not useful energy because you can't transport it from one place to another and do work while you're transporting it. But if you have a hot cup of coffee and an ice cube, if you make a particular machine, you can take that and produce electrical energy, physical energy, or whatever. But then you'll end up with cool coffee and an ice cube will turn to water, and now it's useless energy. Okay, that's entropy, and a lot of people who are believers in God are stymied by the fact that they don't differentiate between thermodynamic energy and information. Because thermodynamic energy is the reason why there was so much energy at the beginning of the universe, assuming the Big Bang model. God may have done it without a Big Bang, okay? But I'm saying that the whole universe is in a state where it's going from an improbable state to a more probable state. It's always going to the more probable state. And as you go to a more probable state, you lose information, because information is improbability. So if I, for instance, have a book, say it's got the classical Shakespearean sonnet on it, I have not only changed the probability of that book by all that information, I've changed the probability of the universe, right? Because that piece of information belongs in the universe, and so the universe can't be any less improbable than that book is. Okay, and I'll get to a little bit of that a little bit later. But I just want you to realize there's a difference between information and entropy, thermodynamic entropy. And as information scientists, we talk about. I'm not professionally that, I was an electrical engineer, but they'll talk about entropy for information as there's a very similar definition, and information has the same characteristic. Information can be lost, but it cannot be gained other than by a supernatural agent. And for that reason, there's a good reason to think that we are supernatural agents. That in other words, if we have a free will, we have to be supernatural. If you are totally naturally driven, then your will could be predicted from ahead of time, right? But to say that we have a free will is to say that we have a supernatural, we're a supernatural entity. Piercing the universe, more or less. Okay, that's a whole other discussion. But I just wanted to, bring up that possibility. Okay, entropy always increases because systems always proceed toward the more likely state. That's what it intuitively means for something to be likely. Is that it's what's going to happen. When you get a weather forecast, they say 80% chance of rain. That's the more likely things that it's going to rain tomorrow. Okay, and things always go from the unlikely to the likely. Now, if you run that backwards, run it back just like people do with the Big Bang. They say it goes back to this explosion. If you go backwards, the universe was more unlikely yesterday than it is today. The universe, unless there's supernatural agents reversing that, like us. Okay, but you go back and back and back, and if for a naturalist. A materialist naturalist, they would say that you go back and you end up, this law would apply. There is no supernatural force going on it. So as you go back in time, the universe gets more and more improbable. What does that mean? That means that the most improbable state that the universe ever was or will be in was at the beginning of time. And when something's in a super hyper improbable state, that's what we call a miracle. The beginning of the universe had to be a miracle. It had to be because it was the most improbable state. For a naturalist, now, it could be that we're changing it because of our supernatural agency into the universe, but certainly, a naturalist can't claim that. So they would have to say that the beginning of time was the most improbable state that the universe was ever in because of the law of entropy. And I'm talking about the informational law of entropy, not the thermodynamic. It's also true for the thermodynamic, right? The beginning of time was where the material was in its most improbable state. It was a ball, if that's what something like the Big Bang is true. So, systems always progress with time from an unlikely state towards a more likely state. An increase in specified information is, by definition, more unlikely. Okay, so that means that you can't have an increase in specified information. It has to be more information in the past, and we're losing that information as we go forward. Therefore, information will always be lost as time progresses. That's basically what I was saying. From a naturalist perspective, there can be no information in the universe at the beginning of time. Otherwise, there's no need to explain unlikely things. I mean, you can imagine going up to a person and saying, well, when the universe exploded, human beings exploded out of it, all ready to go, IBM computers and cell phones and digital radar and whatever. They'd say, that can't happen. That's too unlikely. No, that's exactly what you have to believe if you're going to be a naturalist, is that the beginning of time, it wouldn't be the digital computers and the human beings, but it'd be the things that caused the digital computers and the human beings, which is even more unlikely than the human beings themselves are. Okay? And this is the kind of thinking that a naturalist just has to get wrapped up in, because they don't want to have a supernatural beginning. And any time that they don't have to explain it, they bring in a supernatural possibility. Right now, what's called the many worlds theory is very popular. Many people believe that because they look at how unlikely our universe is, and all this constants of physical constants that have there's no reason why they should be, why the force of gravity should be the value it is. It just is. And the strong nuclear force and the weak nuclear force and the electromagnetic force, all those forces just are what they are. And if they weren't what they are within a very, very tight tolerance, we wouldn't be here. And so the first thing you look at and say, wow, that makes the universe a very special place. They say, no, we just happen to be one of an infinite number of universes that have had those values and made things happen the way they do. There's a whole lot to say about that, but that's for another discussion. But you see the problem we're having there? Okay. Therefore, there cannot presently be information in the universe, because we would never have had it in the beginning. But we do have information. We know we do. DNA is information. All these books that we've seen, and the buildings that you look around, and all these structures, and the butterfly's patterns on his wings. All these things are specified information. I already opened this up. If anybody here experienced the shuffling and wants to admit it, you can do it? Okay. They're slippery. Yeah, when you buy them from the store, a deck of cards is in a particular organization. Now, I want to propose a question to you. If there was a combination of a deck of cards that if we got them in that combination, just lined them all up and got them in that combination, it would spring to life, would we have found it? What do you think? Would we have found it? Casinos are shuffling cards all the time. People are night watchmen are sitting at their desk and they're playing solitaire on their computers. Every time they do, the computer shuffles the cards. All those shufflings, if one of those shufflings caused the cards to spring to life, would we have found it? Most people say yes, right? The number of times we've shuffled cards and everything else, there's just no way. Now, that's the thing. I want you to know that the answer is zero. It's not exactly zero, but it is so close to zero that it would be perverse. It would be absurd to say anything else. And thank you for giving that statement. I'm sure most people are thinking that if you have these cards and you put them in, I just shuffled them again. Maybe I'm getting them in that shape. Okay, there. Maybe they'll spring to life. Well, watch this. I've got to show you how this actually works. The number now. Some of you are mathematically inclined, so you know what 52 factorial is. And I'm going to ask you a question. But those of you who have a mathematical understanding of what it is, I want the intuitive understanding. I want what comes from your gut. I'm going to see if Dr. Baugh would give us a book from the museum if you get the answer to this question. And the way you have to get the answer is it's more than 80,000. Okay. If you think that the next thing I'm going to put up there, which is 1,000 times bigger, 80 million, if you think that that's the answer, you got to raise your hand, okay? And if you raise your hand and that is the last one, you get the book. But maybe you want to go on longer and see, okay? So I'm going to go for 80 million. Anybody want to raise their hand? Think there's 80 million or less chances or permutations, it's called, of a deck of cards? Okay, we don't have any hands raised. How about 80 billion? Anybody want to go for 80 billion? You guys are, okay. About 80 trillion. Think there's more than 80 trillion combinations of a deck of cards? What about, okay, so quadrillion we're at. That's 10 to the, trillion is 10 to the 12th. That's 10 to the 15th. 3, 6, 9, 12, 15. Yes, 15 zeros on, well, actually there's 16, but I'm saying 80 and then 10 to the 15th, okay? So it's 10 to the 15th. Now we're getting up to the quadrillions. How many have known of a quadrillion? Have you ever seen a quadrillion? Is that the last? We'll go to the next one. Is that going to be the number of cards? Quintillion. No hands? Okay, well, all of a sudden it's going to come to the answer, and you're going to also, I'm going to say, well, that was it, and nobody's going to get the book. So somebody's got to raise their hand. Sextillion, septillion. And these numbers are from Wikipedia, so they're actual numbers. Octillion. Now you'll notice that now it's 9. Decillion. No hands? Undecillion. Yeah, this is 52. 52 factorial. 51. Right. Which is what the chances are. I'm wanting your gut reaction, not your mathematical prowess. Okay?
No, that's elementary.
Okay, well still. Okay, undecillion. Okay, we're going to get to it and nobody's going to get it. Dodecillion. Tridecillion. Quatordecillion. Quindecillion. You can kind of tell you probably, if you're going to stop on one, you want to stop here because it's going to be the end of the, right? Yeah, so this is a good place to stop. You're going to stop? Okay. We got a bold person here. Great. All right, so, but nope, it's not the end of it. Septendecillion, which is where we get the number September from. Septem means 7, which it's the 9th month. You know why? Because in the middle of the summer, 2 months were added. For August and July, named after Julius and Caesar Augustus. But otherwise, September should be the 7th month. But okay, September. So the next one is going to be Octodecillion, and the next one will remind you of November. Novemdecillion. Are we? With just one hand, she may be the winner. No, wait. You can't be the winner. You wasted too soon. Okay, you still can do it. Okay, Vigintillion. Okay, you're gonna raise your hand. Okay, I don't know what the prize might be, but you do win because that's the end of it. Wikipedia doesn't have a name for that, but that is it. 52 factorial is 8 times 10 to the 67th power. If you count the zeros there, including this one here, that'll be 67 zeros. 8 times 10 to the 67th power. So that is a huge number. Now, what we're going to do is we're going to try and see what that would mean. Here we've got, take 1 trillion people, okay, that's 10 to the 12th people. That's more people than have ever lived. And you give each person a trillion computers. That's, that's a lot of computers. Now we've got a trillion computers. Let them shuffle the cards at a rate of 1 trillion shuffles per second. Well, what's a trillionth of a second? You know what it is? It's a picosecond. Light goes around the Earth 7 times in a second. And a picosecond, it goes, in a nanosecond, it goes a foot. A picosecond would be a 1,000th of a foot, just like that. That's a picosecond. So we're doing every picosecond, we're shuffling the deck of cards, and we're going to do it for 1 trillion years. Under these conditions, your chance of encountering a specific permutation in the deck of cards is 1 in 1 trillion. Still, after all of those, and here I'll show you. Whoops, where did I? Let's see if I can get here. Okay. I guess I did it right here. So odds are 1 in 1 trillion. Here's what it is. 1 trillion people is 10 to the 12th. 1 trillion computers, 10 to the 12th. And since each person has 1 trillion computers, that's 1 trillion computers shuffling a trillion times per second. That means in every second you get 1 trillion shuffles. And then you do that for 1 trillion years. Now you have to convert from seconds to years, which is 10 to the 7.5. Trust me. And then I do it for 1 trillion years. That's 10 to the 12th. So you've done trillion times 30 million, basically, about 31 million. And that number is the number of permutations that you would see if you did that. And if you did that, you would have 10 to the 55.5 different combinations or permutations. The number 52 factorial is 10 to the 67th. It's actually 67.9. And so you subtract one from the other because you're doing exponents, and you get 10 to the 12.4. Your chances are less than 1 in 1 trillion of finding it after doing 1 trillion computers, 1 trillion people having 1 trillion computers, doing 1 trillion times a second for 1 trillion years, and you still have got 1 chance in 1 trillion of finding that magical one that makes those cards come to life. In other words, we have not even approached all the combinations of a deck of cards being done. Because you can see these are nothing like, if you put some real numbers in there, the deck of cards wasn't invented until a few hundred thousand, maybe 1,000 years ago, whatever it is. All these numbers would be much smaller, and still, that's all we would have done. Now, does that amaze you? It makes you realize that we're way off when we try to understand something like that. Who would think that these 52 cards would be that unlikely you'd ever have the combination I hold in my hand here has never happened. When you get in a car, your chances of having an asteroid hit you are more likely by far than that this combination has ever existed. But they say one of the things you have to do is to take all of the cards, put them on spread them out where they're not even touching each other, and do this, because otherwise, just shuffling back and forth like this doesn't do a real good job of shuffling. In fact, There's a thing called the perfect shuffle. You may know it. If you take a deck of cards and you exactly go ping, 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 and you always put the one on top of the other the same way, one of them was maybe first or the was second, you will eventually come back to the same deck you had originally. It's called a perfect shuffle. And so you don't want to do a perfect shuffle. You want to do something a little less. You want when you cut it to spread them, you want to not get it in the middle and so forth. But that's why in a casino, they're told that they have to take the deck out, scramble it around, put it back together, and then start from there. I hope you're properly amazed at how unlikely that is. You want to see another combination? There, whoops. That's another that's never existed before. And there's another one. And there's another one. Never happened before. I can be dead sure of that because the chances are so small that this has ever happened. Assuming they were random to start, you'll never hit them. And I could shuffle them, and when we're talking about things like Bitcoin, it talks about these kinds of things. Now, this is only 26 bits of information. Bitcoin has 256 bits of information. It's a lot more. You have heat death of the universe before you'd find a random combination. But you see what I'm saying? I want you to realize unlikely things are really unlikely. You might as well say them there's zero. We will never find all the combinations of this deck of cards. There may be one that would spring to life. We'll never know because we'll never get them all the combinations. Okay? We're doing one key per second, and we've got about a 31 key keyboard. And I chose that specifically. It's big enough to get all 26 characters, but the main thing is we want to be around the square root of 1,000. Which is 31 point something. 32 is 1,024. So 31 point something. That means that we got the M. Okay. What we're trying to do, I'll try to explain what we're doing here because we're running out of time a little bit. But we're trying to spell. Methinks it is like a weasel. And that's what is written up here. Methinks it is like a weasel, which is a phrase out of a Shakespearean, not a sonnet. It's out of Hamlet, I believe it is. They're looking up the clouds and they're saying, "Oh, that looks like a prince." And one says, "Methinks it is like a weasel." And so this is what Richard Dawkins used in his book. I believe it was, which one was it? Was it Climbing Mount Improbable? I don't remember which book he wrote this in. No, it's the Blind Watchmaker. He wrote this in. And so we're going to try and spell methinks it is like a weasel, as he said, and see if we can do it. Well, we got the M. Now, it won't, in order to get the next letter, you have to get the M and the E, right? Because it's not enough to get just the E. We already got E's, I believe. You see any E's? No, maybe we didn't. Okay. But we got to get the M and the E. So let's speed it up a little bit here. So now we're doing, we've gotten up to 400 characters. So we actually got the ME a little soon because we shouldn't have gotten until about 1,000 characters. But this is really random, and so you get what really happens there. Okay, so let's double it. We'll just keep doubling it. There's 8. Now the next one shouldn't happen until around 30,000. Well, we got a head start because we already got 2 characters. No, it doesn't matter, does it? That's the gambler's fallacy. Doesn't matter. It's still going to take it that long. Okay, we're getting up into the audio range here. We got ME. We're going for MET. Okay, our typing rate is 64 characters a second. 125. I went down from 128 to 125, so we keep on multiplying it to 1,000. 250. See that we occasionally get a lot of M's. We occasionally get an ME, but we haven't gotten an MET yet. The characters are getting smaller, so you can get them on the screen. There's 500. Going for 1,000. Would you have thought that you would find MET by now? Is that hurting your ears? Okay. There's 2,000. We'll go out of the range of hearing pretty soon here. Oh, does it? Well, I think I'm getting enough. They're putting their fingers in their ears already. So, 4,000. Okay. We got it. We got MET right about on time because we should have had 100,000 should happen at 30,000. So that one took a little while. But you see what's happening here? It's just taking forever. That's 8,000. So we keep on going here. There's 8,000. You put your fingers back in your ears. 8,000. Okay, now it'll go out of most of your hearing. There, some of you can hear this, but most of you cannot. You can hear it? Yeah, younger people can still hear it. If you remember the old TV sets, they had 525 lines at 30 characters, 30 lines per second. That's 750. So this is 16,000, just above that. Some people, when you turn on your old TV, that sound, that's the sound you're hearing there. But now you won't be able to hear it, for one thing, because we're doing 40 kilobit per second sound, and we're up above the Nyquist frequency, so you won't be able to hear it. That's 30,000. And it's still keeping up, but we're not getting that. It should go to about 1 million. Oh, it did. Right about on time. METH. Okay? Now you're going to have to wait a long time, because it's going to take 30 million before that will happen. I can put this back. Okay, there we go. But so the thing I want to point out here now is I'm just going to let this thing run in the background, and I've got a second program, because some of you who are critics are going to say, well, wait a minute, this is one monkey. So what if you can't do it? We got bazillions of monkeys. The infinite monkeys theorem says there's a lot of monkeys. So let's just leave this running in the background. I think I can open up the window here, and we'll go back to this thing here. It's still running, and we'll go to another program here, which is called Monkeys, and monkeys.exe. Where is it? There it is. Okay, and if I bring this down, you'll be able to see that running in the background. Okay, so that thing's still running, and maybe we'll get something, but probably not. Okay, this one should put it to sleep. There's no chance that this will happen, because what we're going to do, first of all, I'm going to show you what happens if you type 4 characters a second. Here's typing 4 characters a second, and we're typing Genesis 1, I think a little bit of 2 maybe. In the beginning, God created the heavens and the earth. And so at 4 characters a second, it's pretty easy. But now we'll stop it. And now we're going to do what we were doing before, where we're going to have to do the I, and the IN, and I, and so forth. But we can play with things. We can say how many monkeys. We can say how many keys per second, and say and we'll have a scale on here that we can make it 1 second equals 1 second as it is now. So we're doing the same 3 that we were doing earlier with the deck of cards. All right. So here we go. Okay. Now this is doing mathematically, so it can actually do pieces of a character. So when you get to 30 seconds is when the characters will go to 1 character. There's no characters yet. Maybe with the first one we'll just let it go to 30 seconds so you see what I'm talking about. Well, no, let's make it go faster. You'll be able to see it anyhow. Okay, let's make it, instead of 1 monkey, let's make it 1,000 monkeys. And begin it again. And you can see that it gets the I, and there's the N. Wow. Maybe we can type out in Genesis 1:1 after all. But it slows down. Why does it slow down? Because it has to type IN 30 times to get the next one. Okay? So we're going to be stuck there. And you can see it's getting there, 2.87, 2.88. When it gets to 3, it would put up the third, which is a space. Okay? Space character. Well, let's get 1,000. Let's go to a million, a billion, a trillion. Let's go to a trillion monkeys, okay? And we'll start it again. You get in a space. Oh, there's the B. Wow. Look, if we get the B that fast, maybe it'll... But no, it slows down. It's the very same behavior. No matter how many you get on there, it'll go... And then the last one's just going to take 30 times as long as what it took you to get that one. So we're coming up on the E there, 85, 86. Maybe I should wait for one so you see what happens. 90, 92, 94. And it's getting slower and slower as it goes. 96, 98, 99... 9 characters, so we got the E. Now we could start over 9.03, and it's going slower and slower. So it's going to take 30 times as long once it gets to the end of that character. Okay. Well, okay, that's only a key per second. Let's go to. We're getting late, so we better get in here. Let's see. 1 million keys per second, billion, a trillion keys per second. What's it going to do? In the beginning. That's it. You got it. So we got the G. But now you have to sit and wait, just like you waited before. It doesn't matter how many you put in there, that next character is going to take that long. Now we've got a trillion monkeys typing a trillion keys per second. Let's kick up the time, okay? Instead of doing it in real time, let's go 10 seconds. We'll go to at least a day, a year. Okay, here's a year. Now you can see we're going back just 2 years. 3 years, 4 years, 5 years, 6 years, and it did in the beginning God's space, and it slows down the same way. You see what I'm saying? People don't realize that when just like when the monkeys and typewriter, we got them M, and then we just litter with M's. You can see all the M's in there. But getting the ME, very seldom. And MET, that's once in 30,000. METH is once in a million. METHI is once in 30 million. Same thing's happening here. Okay, so let's go all the way up to the top here. Now I hope the computer can handle it, because we're going to be stressing the computer when we do this. But we'll go up 10 years, 1,000 years, a million years, a billion years, a trillion years. We could have gone beyond a trillion monkeys. I forgot. 10 to the 18th, 21, that's 23rd, 36, 42, 48, 51, 54, 60, 63, 70, 10 to the 70th. We're getting up to 10 to the 80th. That's the amount of particles in the universe. Okay, so you have all the 100 billion galaxies with 100 billion stars in each one, and we're taking all the particles, all the electrons in those, which is 10 to the 80th, and here's what it will do. We got a little ways. We actually did get the first verse, and we're working on the second. The earth was with, and that's it. And once again, it slows down. That's as fast as you're going to get going. So let's try going all the way up to. We can go. Let's see. Oh, we got to take this up. Oh no, we're all the way up to everything. I think you can see that we're just not going to get anywhere. Oh, there we go. Oh,
Jim, your computer.
Oh no, we're overheating it. Oh. I better stop. We're overheating the computer. But okay. You see what we're saying? It doesn't matter. You can do a Google of monkeys typing a trillion keys per second for a trillion years, and that's as much as you got. You see the answer with the deck of cards. Realize we will never, ever get anything like what is said that we would get with. Here, I'm going to stop these for a second here. What I was going to do if we had time, which we don't, is show what's going on with your DNA. Now, this isn't your DNA. This is every DNA of every life form that exists, down to the fungus, a single microbe, take the simplest life form that we know of. It uses DNA replication, transcription, translation, and ATP synthase animation, ATP synthase in order to produce the energy that we need. And there's a bazillion other things too, of course, but it's just not going to happen, okay?
Absolutely awesome. Let's give it up.